Hey, I would like to review our last class. In our previous session, we talked about the multiple linear regression. Linear regression aims to approximate data with a straight line or plane, uh, which makes it possible to predict unknown data. When we have data points like this, we wanted to draw a line that follows them. This could be expressed using variance, and covariance, but we wanted to apply this to case with more variables as well. We call the x variable the explanatory variable and the y variable the objective variable. When there are many explanatory variables, it is called multiple regression. And we wanted to approximate y using calculation with beta 0 through beta p. The calculation method was still the least square method where we wanted to find beta 0 through beta p that minimize the sum of square of the differences between predicted variable and actual values. Specifically, we could calculate this using matrix X. We go to here. We could calculate this beta using a matrix X by explanatory variable with a column of ones in the first column and a vector Y of objective variables. Another topic we discussed was the coefficient of determinant. Linear regression can be applied to almost any data, but we don't know if it's good or bad. The coefficient of determination can measure this goodness of fit. It takes a value between 0 and 1. A coefficient of determination close to 1 indicates the actual values, the predicted values are close, showing high approximation performance. A coefficient of the determination close to 0 indicates the poor approximation performance. Despite the term explanatory variable, they do not necessarily explain the objective variable well. We cannot determine if there is a causal relationship with this method alone. We also talk about how outlier can easily affect the results. So, the in-class report for lecture 3 like this. First, okay. So, can we always predict the objective variable accurately from explanatory variables by applying linear regression? The answer is no. Regression can be applied even to completely scattered data. In such cases, we cannot necessarily predict the objective variable accurately from the explanatory variables. Here. Therefore, if even if linear regression works well, we cannot determine whether there is a causal relationship between the explanatory variables and the objective variable. So this is correct. Also, the result of linear regression are affected by linear, and when linear regression works well, we must carefully consider the reason for this. As I mentioned earlier, since we cannot determine whether there is a causal relationship, uh, it might just be coincide that such a linear relationship worked well, so we need to think about the reason. So the second option is the correct answer. Okay. Okay, let's go to the next question. Next question is for the coefficient of determination. For the linear regression model obtained by the least square method, the coefficient of determination is between 0 and 1. So coefficient of determination cannot exceed 1. The higher the approximation performance, the closer it gets to 1, and the lower the approximation performance, the closer it gets to 0. The predicted value and the actual values perfectly match when the coefficient of determination is 1. So the second option is the correct answer. Okay, next one. For the Python code problem, as written in the feedback, so A dot T is the transpose of the matrix A, NP, numpy dot linear algebra dot inverse. A is the inverse of A. NumPy dot linear algebra dot determinant is the determinant of A. Finally, NP dot linear algebra norm A axis is 1 is a normal which law. So to output the inverse matrix, we need to use np dot linear algebra dot inverse A. The last problem. This asked you to estimate using the least square method and calculate the coefficient of determination. Okay, let's get code. So we use, yes, we need to use here, we need to use this code, but uh, we need to define simple regress and import numpy np. Okay, execute. So, looking at this code, as usual, it follows the flow of providing data, analyzing data, and the output, the result. Specifically, it estimates parameters using simple regression, calculates the predict values from the explanatory variable using these estimated parameters, and then calculate the coefficient of determination using these predict values and the actual values. Since the data is always provided here, okay, so copy and paste. You can calculate the coefficient of determination by copying and pasting this code. The output result is about 0.83. So the answer is 0.83. Okay. That's all. Okay. Okay. Let's review session 4. When okay. When using the least square method to determine parameters for multiple linear regression, we needed to calculate the inverse matrix XTX. Uh, Mathematically, an inverse matrix doesn't always exist. And when the determinant is zero, there is no inverse matrix. This situation rarely occurs in practical problem, but when the determinant value is small, issue can arise. Specifically, when calculating the inverse matrix, we divide by the determinant, meaning we use the reciprocal of the determinant. If the determinant is small, division by a small number results in very large numbers. The determinant value becomes small in specific situation here. Uh, when there is limit data or when there is a strong correlation between the columns of the matrix. Uh, this occurs, uh, this occurs when explanatory variables are strongly correlated with each other. This situation was called multicollinearity. This problem was when explanatory values has this property, the determinant becomes small and parameter become large. To address this, there is a method called Ridge regression that adds the sum of square here of parameters to prevent coefficients from becoming too large. By adding this, we effectively calculate the inverse of xtx Yeah. We so we effectively calculate the inverse of xtx with lambda times the n lambda times identity matrix added. This matrix is always regular, making calculation possible with any data. This is why it's called regularization. Uh, the rich regression algorithm, okay, itself is simple. Calculate the means, calculate averages, subtract these averages uh, from each data point to create centered matrix X tilde and vector Y tilde. And use these to calculate the parameters like this. Okay. Another method. Another method adds the sum of the absolute values of parameter instead of sum of square. This is called loss regression, and it's particularly effective when there is less data compared to number of parameters. In the loss regression, okay, yes. In that regression, we use algorithms with soft threshold functions to obtain solutions. Uh, like here. This is a soft thresholding function. First, we calculate the average and subtract them from the data. Unlike rate regression, loss regression doesn't allow direct calculation. So we gradually approach the true value by repeatedly updating parameters and consider it the answer when uh, the answer when updates produce little change. The large we the large okay, so the larger we make the regularization parameter lambda, the more coefficient becomes zero. By choosing appropriate value, most parameter become zero, leaving the only important parameters. For example, in the graph, the blue line, so this one is beta 1, has the largest value, uh, suggesting that the first explanatory variable has the greatest influence on the object variable. That was the topic of the discussion. Okay, let's examine the problem. So in class report for lecture 4, okay, first, first, it's correct. The linear regression estimate model coefficients by minimizing the sum of square errors. The next option states the ridge regression is applied when there are few expanded variables, while a simple least square and last regression are used when regression is not needed. This is completely wrong because last regression is a regression method. Also, the description last regression is suitable for cases with much collinearity. Simplistic square is suitable when there is no much collinearity, and rich regression is suitable when variable selection is important. Is not accurate. Rich regression is suitable for a case with much collinearity. Because of these differences, the choice of method does not depend on personal preference. Uh, this one. So yes. The choice of method doesn't depend on personal preference, but on the characteristic of the dataset. So the correct answer is the first option. Okay, next one. Rich regression is a method that makes the estimate coefficient smaller by adding the sum of square here or the coefficient to objective function. So the second option is correct. On the other hand, Lask's regression is here. Loss regression is a method that adds the sum of absolute values of the coefficient to the objective function. So the first option is the correct description. Okay. The next problem asks us to estimate values for given data. While the curve performs so last okay, okay, execute. Okay, here. Okay, well, so the code perform various processes, the flow of preparing the data, executing rich regression, and outputting the result remain the same. We just need to use the necessary parts. Okay, so in this case, we have this data. So copy and paste. Okay, we obtain that. As a result, we find the intercept is 0.82 and beta 1 is about 1.59 and beta 2 uh, is minus 0.55. So the answer is like that. Similarly, we run that regulation. So we copy slash function. So same. So this one. Okay, the same. If we run last regression, we get the result like that. So we get the result showing that the coefficient for the fourth explanatory variable is largest. Therefore, when asking which explanatory variable is most important for explaining the object variable, the natural answer is the first one. Okay. The last problem is somewhat special. It asks, assuming the number of data point is much larger than number of the expanded variable, which of the following situations might make it impossible to determine the multiple linear regression coefficient. The first option is there are many different data points, but two of data points have exactly the same values. The second is among multiple explanatory variables, two explanatory variables take the same values across all data. When we consider the matrix X on slide 4, so this one. Uh, so having some same data correspond to uh, having the same rows, having the same explanatory variables correspond to having the same columns. When there are identical columns, since there are p plus, so the p plus one columns, linearly dependent elements are mixed in, and the rank of the matrix become less than p plus one. Therefore, in the case of the second option, so this one, the multiple regression parameter cannot be uniquely determined. As for the first option, while it could be a problem if there are few data points, the problem state says the number of data points is much larger and there are many different data points. So, when asked which one is more likely to cause problems, the second option is the answer. And that concludes explanation of the previous problem. Whew. Okay. Hey, I'd like to add. Okay. I'd like to address the comments that was made. Hey, the comment mentioned. Uh, okay. Okay, so I found it interesting that when recording calculation result in binary, they can be slightly different from the actual calculations. Uh, which I believe refers to when we calculate an inverse matrix in Python and multiplication with the original matrix didn't result in exactly the identity matrix. This seems to be more comment than a question, but let me provide some additional information just in case. The slightly deviation from expected calculation isn't primarily caused by using binary numbers, but rather by the fundamental limitation that each data value has a restricted size. For example, um, let's say we can only store up to 3 decimal parts. Here, 3 decimal place. In the decimal system. If we want to calculate 1 over 3 times 3, of course it's 1. We first calculate 1 over 3, which equals to 0.33333. However, since we can only store up to 3 decimal places, it gets stored internally as 0.333. When we multiply 0.33 by 3, the result is 0.999. So what should mathematically equal 1 becomes 0.999 instead. This is what happens inside computers. The same thing happens with larger numbers of digits, which is why calculation results may not exactly match the mathematically expected values. Up to 3 decimal places is just an example for explanation. More accurately, numbers are stored as binary floating point numbers with a certain number of decimal places. There are also limitations on the exponent part, but going into the discussion would be like starting another class. So, for details, please refer to Wikipedia explanation of IEEE 754. Okay, next question. Okay. Okay, so in last regression, it was explained that the sum of the coefficients can be reduced to nearly zero, which has the effect of selecting the more important explanatory variables. Why doesn't ridge regression have this effect? I'm confused about how just changing from the sum of squared coefficient to sum of absolute values in the objective function can create such a different effect. Okay, good question. Hmm. Let's first consider a simplified case with one-dimensional data where the mean is zero. In other words, we are looking at the problem of approximating with a line through the origin, where the intercept is zero. For ridge regression, we add the sum of square of parameter of the objective function, while for last regression, we add the sum of absolute value. With ridge regression, we can differentiate the function and find where the derivative equal to zero. After working through the calculation, we get this one. As lambda increases, beta certainly gets smaller, but it never becomes exactly zero if s is not equal to zero. For last regression, the objective function contains absolute values, so we can't differentiate it conventionally and must use differentials. Using the discuss from slides to 28 to 30 for the slide, where sk becomes s and sigma k square becomes sigma square, we get here. Here s lambda is a soft thresholding function, like that. This becomes exactly zero when the input falls between minus lambda to lambda, as shown in this figure. Therefore, so look at here. Uh, so when when lambda is larger than s, beta will always become exactly zero. This is a major difference between ridge regression and Roth regression. For multi-dimensional data, we apply the same argument to the partial derivative of each beta 1, beta 2, blah, blah, beta 3. While not exactly the same discussion, the reasoning is similar. This is why coefficients in loss regression can become exactly zero, while in ridge regression they are less likely to become zero. Uh, Delving deeper, the partial derivative of the objective function consists of the Euler term derivative and regularization term derivatives. In ridge regression, the derivative of the regularization term to beta k is zero. Uh, in contrast, for last regression, the regularization term is absolute value of beta k, so its differential at beta k is zero is the interval from minus lambda to lambda. So the objective function reaches its minimum when its partial derivative is zero. For ridge regression, when beta k is zero, uh, the partial derivative of the objective function is zero only if the partial derivative of the error term is also is zero. However, for last regression, when beta k is zero, the partial derivative of the objective function can be zero as long as the partial derivative of the error term falls within the range minus lambda to lambda. This is why last regression can selectively set parameter to zero. That's the background for the difference. Okay, and it's today's lecture. Okay, today I will talk about k-nearest neighbors method. From this lecture, we will consider classification problem. You will learn the classification problems and How to handle one approach called the care nearest neighbors method. Uh, Within this method, there are parameters that need to be determined. One approach to determine these parameters is cross-validation, which I will introduce. First, let's talk about classification problems. As the name suggests, classification aims to categorize data, classify data. For example, as we discussed in the previous class lecture, we might want to identify whether an animal in an image is a dog or a cat. Determine if an email is spam or normal. Distinguish humans from other objects in image, or determine whether cancer is uh, a problem or no problem from genetic data. They are all classification problems. Images and text are difficult to handle in their raw data, so we convert them into numerical representation. For images, we correspond them to sequence of numbers and label them as human or not. For example, we might label human as 1 and non-human as 0. Specifically, we look closely at the black and white image. It appears like a mosaic, like that. In the case of black and white image, the mosaic is represented in grayscale from white to black, and we assign number to represent the brightness. For instance, if we assign the number 186 to certain color, this one, uh, and then correspond the numbers, for example, 120, so, and here 124, 103, 38, 134, blah blah blah, to the mosaic pattern starting from the top to top left. The image can be represented as a matrix of numbers, like that. If arrange these numbers row by row, we create a very large vector. Of course, this applies not only to black and white images, but also to color image. Color image can be divided into RGB values, red, green, and blue information. And we can create number corresponding tables for each by creating tables for red, green, and blue separately and viewing them as a single vector. Even color images can be interpreted as numerical vectors. We attach labels such as doc to these vectors. For example, if we correspond a doc to 0, we want to associate this vector with value 0. Since such high dimensional data is difficult to handle, let's consider it in a very low dimension, such as two-dimensional data. Let's say the data is distributed as shown here, with red data and blue data. In this area, we want to be able to classify them effectively. Okay. I'll now explain how classification is performed using the k-nearest neighbor method. First, let k be a natural number. Let's assume we have data x1, y1, x2, y2, blah blah blah, xn, yn. Here, so xi could represent vector data such as the image we discussed earlier, and yi is a corresponding label. For example, in distinguishing between dogs and cat, we might assign label 0 to dogs and label 1 to cats. Let's say we have n pairs of images and labels. Now, suppose we are given a new data point, x star, and determine the label by majority vote of these k points. In other words, we take k data points, and if there are more zeros, we classify it as zero. If there are more ones, we classify it as one. This method can be easily applied even when there are multiple labels. If there are m labels, we still choose a natural number k, and when data points are associated with labels from 0 to n minus 1, we determine the label of new data by majority vote of k closest data points. Okay, now is around 15 minutes, so let's take a break. Okay. Okay, let's restart. Let's try this in practice. Suppose we want to determine the level for the star symbol. Oh, here. Level 0 data is red data on the right. And level 1 data is blue data in the upper right, left. And level 2 data is green data in the low left. The star is somewhere in the middle, and the question is how to classify it. For k is 1, uh, we only look at the closest data point here. Which one is closest to this star? So which one? So this one is closest to this star. It's green data. Therefore, the label at the star's location is classified as green. Meaning it belongs to second class, so class 2. Where about when k is 5? Looking at the 5 closest data points, so here, 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 here. Three of them are green. And two of them are blue. So green is still the majority, and we predict it as green. This is K-nearest neighbors method. Let's consider how the result change depending on the choice of k. The smaller the value of k, the more the prediction is influenced by nearby data. So in areas where data is mixed, decisions are made based on only the closest data point. On the other hand, as k increases, we are averaging over more data points, so sensitivity to local variation decreases. The boundary that divides set by levels is called uh, decision boundary. This, yes, this one. Using this term, a small value of k makes the decision boundary sensitive to the data. For example, if an area contains isolated green data points, a region around it will be classified as green. Similarly, if there are solitary blue data points, the area around it will be classified as blue. Conversely, as k gets larger, the decision boundary becomes smoother. Even if there are isolated data points, taking the average of surrounding area increases the influence of other data, thus suppressing local variation. Okay. Let me now address a detailed point. What to do when there are equal numbers of levels among the key data points in k-nearest neighbors method. This can be considered a case where the data is on the decision boundary, but the handling is not standardized across reference books. In this course, in this lecture, when there are equal numbers of levels, we simply choose the one with the smaller number. That is, if levels 0 and 1 appear equally often, we choose 0. In the scikit-learn machine learning library, the implementation of k-nearest neighbors method, it first selects based on the smallest distance. And if distance are also the same, it chooses the level with a smaller number. Okay. What does the algorithm for look like? In k-nearest neighbors method, we need to find the k closest item. So we need to calculate distance to determine proximity. The specific steps are as follow. Calculate the distance from each data point to data point we want to predict. Sort these calculated distance in ascending order. Correct the indices of the key data point with smallest data distance. For example, xi1, xi2, the xi3, like that, xik. The k data points closest to z, the data we so that is data we want to predict. The indices would be I1, I2, blah, blah, IK. Finally find the most frequent value among the level correspond these indices. So yi1, yi2, yik. For implementation, NumPy provides convenient functions that make it easy to sort data. The argsort function result in indices that would sort an array in ascending order. For example, if we have a one-dimensional array x like 3, 1, 2, executing np.args.x returns the array 1 to 0. In this specific case, it returns 1 to 0. What this means is the smallest number is at position 1. So x1 is the smallest. Indeed, this is 0 and 1, so this is x1. So this is, which is indeed 1. The second smallest number is at index 2. So 0, 1, 2. So x2 is here, which is 2 in our array. And the largest number is at index 0, which is 3. The 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 bin count next. The bin count function short for binary count can count the occurrences of non-negative integers. For example, if a one-dimensional array y like 0, 1, 1, 3 to 1, 7 is given, executing np.binary count y returns away 1, 3, 1, 1, 0, 0, 0, 1. This indicates 0 appears once. Indeed, 0 is here. 0 appears once. 1 appears 3 times. Indeed, 1, 2, 3. So when 1 appears 3 times. So 2 appears once. Indeed here. Like that. So 4, 5, 6 don't appear. So 0, 1. 0, 0. Combined with argmax function, np.binary count y.argmax tells us that 1 is the most frequent value. Using these functions, we can efficiently implement the k-nearest neighbors algorithm. So the code for the k-nearest neighbors method looks like this. So we calculate the distance between the observed data and the data we want to predict. Uh, Sort these distance in ascending order and taking k items by using slice. When we then get the levels, corresponding to these indices of the nearest neighbors from 0 to k minus 1, and using the function introduced earlier, we can easily find the level with the highest frequency among them. Concrete implementation using NumPy would like this. Let me highlight some important considerations for k-nearest neighbor method. Look at the figure we saw earlier. Uh, the method actually depends on the distance for each explanatory variable. If we compress the x coordinate value, so like that too, at 0.1 times the original values, the data looks compressed as shown. When we apply k-nearest neighbors with k is 5 to this compressed area, we now find 3 red points here, 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 and 2 green data points closest to the star, making red the majority. So the k-nearest neighbors method would classify the star data as red. This was green. So please note that the k-nearest neighbors method depends on the distance for each explanatory variables. To address these issues, one approach is to use Mahalanobis distance instead of Euclidean distance, which can take into account the direction in which the data is scattered, but I will omit the detail here. To summarize what the nearest neighbors method is, it's a technique that classify data based on the levels of the k-training data points closest to data we want to classify. Its advantage include being a simple and easy to understand algorithm that is also easy to implement. No model training is required, and it can handle nonlinear data and complex dataset. Its disadvantage include high computational cost since we need to calculate distance to all data points each time. As I explained earlier, it also depends on the distance for each explanatory variable. Regarding the high computational cost issue, there are methods for efficient calculations such as branch and bound method and approximate nearest neighbor search. But I will omit those details. Since we haven't yet introduced other method, it's difficult to discuss when to use which technique, but we can say that the nearest neighbor method is suitable when the dataset is small and memory consumption or computational cost isn't an issue. Another advantage of k-nearest neighbors method is that it can handle complex datasets where a clear pattern or trends are different to see. A key question is how to determine the optimal value of k for the k-nearest neighbors method. We should find which k gives the highest accuracy, but how do we measure this accuracy? As I introduced in the first lecture, the standard approach is to divide data into training data and test data, and use the test data to evaluate the accuracy to our estimation. However, this method reduces the amount of training data available for estimation. This is where J-fold cross validation comes in handy. I called it K-fold, K-fold cross validation in the first lecture, but here I will use J to avoid confuse with the K in the K nearest neighbors method. Okay. Hmm. Hmm. So why is J-fold cross validation? We divide the entire dataset into J groups, ensuring that these groups don't overlap with each other. First, we use group G1 as test data and group G2 through GJ as training data. Next, we use group G2 as test data and group G2, G1 and G3 through GJ as training data. We repeat this process until GJ becomes a test data. Then we collect and average the evaluation result from step 1 through J by repeating this for different value of k. We can determine the best k. This is a cross validation measure. When applying cross validation to the Kenyas method, we first divide the entire dataset into J group and perform cross validation with different value of K. We select the K that gives the smallest average error data. For example, when we actually run this, the average error rate might be 0.056 when k is 1, 0.0646 when k is 2, and so on. After trying various values k of k, we might find that the average error rate is smallest 0.06 when k is 4 and k is 8. Considering model simplicity and computational cost, it's better to choose a small value. So k is 4 would be appropriate. You might wonder how to choose j for cross validation. It seems that J is 10 is commonly used. Some people consider it optimal to make J equal to number of data points, J equal to n, but increasing J also increases the computational cost of cross-validation. So this decision depends on the available computational time. This figure shows how the average error rate changes with different values of J. The horizontal axis is J, and the vertical axis is average error rate. When j is small, the average rate for different k values vary widely. But as j increase, their ranking stabilize. Therefore, we can see that for the combination of k nearest neighbors and this dataset having sufficient large j, mm, for example, j is greater than or equal to 10 is effective. Okay, let me explain code. So please click here. Let me explain the code. Oh, oh. First, let's prepare the library. Okay. Okay. Let's start by introducing the argsort function for sorting numbers and the binary count for function for counting data occurrences. NumPy has a function called argsort for sorting arrays. If we have an array like 3, 1, 2, and call np.argsort on it, it returns 1 to 0. This means that the smallest number is x1. So 0, 1 here. x1 is 1. The second smallest number is x2. So 0, 1, 2. So this is x2. So x2 is 2. And the smallest number or the largest number is at x0, which is 3. If we change the value, so for example, like that, we obtain 201, indicating that x2 is now the smallest. Indeed, 0, 1, 2. x2 is 2. Indeed, x2 is the smallest number in X. By the way, we can also change in the order of the actual element, not just to get their indices. We can do this simply by using np.sort, which will sort 3, 4, 2 in ascending order. Yeah. Next, we use np.binary count to count occurrences of non-negative integers. If we have an array like 0, 1, 1, 0, 1, 1, 3, 2, 1, 7, calling np.bin count returns 1, 3, 1, 1, 0, 0, 0, 1. In this case, the first element here uh, shows there is 1 0. Indeed, there is 1 0. The second element shows there are 3 ones. Indeed, 1, 2, 3. So there are 3 ones. which we can verify by counting them in the original array. This tells us how many of each number exist in arrays. For k-nearest neighbors, we want to know which number appear most frequently. So we use the argmax function to find out which index has the maximum value. By calling np.beanCount_y.argmax, we can get the most frequent value in y. So 1 is the most frequent value. With these two ready, k-nearest neighbor methods becomes simple. So this is the comment. So resulting in essentially just 4 lines of code. In this code, x represents the date points, y the labels, that z the data we want to classify, and k is the number of neighbors. First, we measure the distance by subtracting z for each data point with x minus z. We calculate the norm for each data point. Once we have the distance from each data point to z, we use argsort to sort them in ascending order, and then take the first k element using slicing. When we get the labels correspond to these k nearest neighbors, and finally determine the most frequent labels using np.beanCount.argmax. For k nearest neighbors with multiple data points, I will prepare a function called knpredict. For cases where you want to know the labels for many data points, when there are multiple data points in Z, capital Z, this function will return the label for each one. This is Python code, so please understand that how it's written. Uh, so let's say we have explain with 3 data points like 0, and each of these 3 data points has been assigned labels 0, 1, and 0 respectively. If we the k-nearest neighbors method with k is 2, we can write code like this to predict the label for data points z1, 2. For cases with multiple data points, we can use a can and predict function we create earlier to predict labels for multiple data points at once. The first output looks like this, showing that the labels for small z is estimating to be 0. This is a natural result since the original training data already contains 1, 2 with label 0. Yeah. Okay, let's move on to class validation. Class validation involves dividing data into groups, performing training and testing with different parameters on each group, and examining the error rate. In first part, please ignore the comment. Uh, First, we divide the data by j to split it into j groups. Using slash slash performs integer division, which means we are truncating the decimal point. Uh, we store the error rates for each group in the error list. We perform the cross validation loop j times. Here. We perform the cross validation loop j times using start and end to define the range of the test data, extract the test data, and create the training data. We make predictions using the training data, then check how many mistakes were made with the test data. We add the error rate to the errors list and return the answer. If we create data like this, and perform cross validation for various values of k, we get the result like this. Okay. In this case, we can see 0.0036 is the smallest error, so it makes sense to choose a small k. In this case, this is case 4. If we choose more data, then k is 10. When k is 10, average error rate is the smallest error rate, 0.0333. So k is the best value. The code below is for reference. Okay, that's it. Now, please work on the in class report for the last page.